A voltmeter is an instrument used for measuring electrical potential difference between 2 points in an electric circuit. Analog voltmeters move a pointer across a scale in proportion to the voltage of the circuit. Digital voltmeters give a numerical display of voltage. By use of an analog to digital converter, the voltmeter in a circuit is represented by an encircled V. Voltmeters are made in a wide range of styles. Instruments permanently mounted in a panel are used to monitor generators or other fixed apparatus. Portable instruments, usually equipped to also measure current and resistance in the form of a multimeter, are standard test instruments used in electrical and electronics work. Any measurement that can be converted to a voltage can be displayed on a meter that is suitably calibrated, for example, pressure, temperature, flow or level in a chemical process plant. General-purpose analog voltmeters may have an accuracy of a few % of full scale, and are used with voltages from a fraction of a volt to several thousand volts. Digital meters can be made with high accuracy, typically better than 1%. Specially calibrated test instruments have higher accuracies, with laboratory instruments capable of measuring to accuracies of a few parts per million. Meters using amplifiers can measure tiny voltages of microvolts or less. Part of the problem of making an accurate voltmeter is that of calibration to check its accuracy. In laboratories, the Western cell is used as a standard voltage for precision work. Precision voltage references are available based on electronic circuits. Analog voltmeter. A moving coil galvanometer can be used as a voltmeter by inserting a resistor in series with the instrument. The galvanometer has a coil of fine wire suspended in a strong magnetic field. When an electric current is applied, the interaction of the magnetic field of the coil and of the stationary magnet creates a torque, tending to make the coil rotate. The torque is proportional to the current through the coil. The coil rotates, compressing a spring that opposes the rotation. The deflection of the coil is thus proportional to the current, which in turn is proportional to the applied voltage, which is indicated by a pointer on a scale. One of the design objectives of the instrument is to disturb the circuit as little as possible, and so the instrument should draw a minimum of current to operate. This is achieved by using a sensitive galvanometer in series with a high resistance. The sensitivity of such a meter can be expressed as ohms per volt. The number of ohms resistance in the meter circuit divided by the full-scale measured value. For example, a meter with a sensitivity of 1000 ohms per volt would draw 1 milliampere at full-scale voltage, if the full scale was 200 volts. The resistance at the instrument's terminals would be 200,000 ohms, and at full scale the meter would draw 1 milliampere from the circuit under test. For multi-range instruments, the input resistance varies as the instrument is switched to different ranges. Moving coil instruments with a permanent magnet field respond only to direct current. Measurement of AC voltage requires a rectifier in the circuit so that the coil deflects in only one direction. Moving coil instruments are also made with the zero position in the middle of the scale instead of at one end. These are useful if the voltage reverses its polarity. Voltmeters operating on the electrostatic principle use the mutual repulsion between two charged plates to deflect a pointer attached to a spring. Meters of this type draw negligible current but are sensitive to voltages over about 100 volts, and work with either alternating or direct current, VTVMs and FEVMs. The sensitivity and input resistance of a voltmeter can be increased if the current required to deflect the meter pointer is supplied by an amplifier and power supply instead of by the circuit under test. The electronic amplifier between input and meter gives two benefits. A rugged moving coil instrument can be used, since its sensitivity need not be high, and the input resistance can be made high, reducing the current drawn from the circuit under test. Amplified voltmeters often have an input resistance of 1, 10, or 20 megohms, which is independent of the range selected. A once popular form of this instrument used a vacuum tube in the amplifier circuit and so was called the vacuum tube voltmeter, or VTVM. These were almost always powered by the local AC line current and so were not particularly portable. Today these circuits use a solid-state amplifier using field effect transistors, hence FET-VM, and appear in handheld digital multimeters as well as in bench and laboratory instruments. These are now so ubiquitous that they have largely replaced non-amplified multimeters except in the least expensive price ranges. Most VTVMs and FET-VMs handle DC voltage, AC voltage, and resistance measurements. Modern FET-VMs add current measurements and often other functions as well. A specialized form of the VTVM or FET-VM is the AC voltmeter. These instruments are optimized for measuring AC voltage. They have much wider bandwidth and better sensitivity than a typical multifunction device. Digital voltmeter. A digital voltmeter measures an unknown input voltage by converting the voltage to a digital value and then displays the voltage in numeric form. DVMs are usually designed around a special type of analog to digital converter called an integrating converter. DVM measurement accuracy is affected by many factors, including temperature, input impedance, and DVM power supply voltage variations. Less expensive DVMs often have input resistance on the order of 10 megaohms, and the resistance may be different for each input voltage range. Precision DVMs can have input resistances of 1 g-omega or higher. To ensure that of DVM's accuracy is within the manufacturer's specified tolerances, it must be periodically calibrated against a voltage standard such as the Western cell. The first digital voltmeter was invented and produced by Andrew Kay of Nonlinear Systems in 1954.